All right, so now we're ready to bring this all together, and we're going to take a look at a situation where we have a phase change and within a calorimeter situation. So in this case here, we have an ice cube that's at negative 12 degrees Celsius, and we're going to place that into some water. The water's at 18 degrees Celsius. The mass of the water is 0.4 kilograms, and the aluminum container is also at 18 degrees when we place that in there. And we want to find out, what is the mass of the cube itself if the, let's see, the final temperature is 16 degrees Celsius for all of them. So T final is 16 degrees Celsius of everything, right? T final 16 degrees, T final 16 degrees, okay? And again, what we're going to do is look at the sum of the cubes because, again, conservation of energy, thermal energy lost by one is gained by the other. And so in this case, it's actually the ice cube that is going to be receiving the thermal energy because, it's 18 degrees here, right? This water is going to 18 degrees and it's going to melt the ice cube and then change its temperature. So when we set up the sum of the cubes for this one, we have to consider the ice cube as being an ice cube, and then in the phase change, and then also once it becomes water. So if you look at that here, we have the mass of the ice cube times the specific heat of the ice cube, T final minus T initial. This is when we're dealing with the ice cube having to go from negative 12 to 0 degrees. So you'd have the temperature final is 0 minus the initial temperature of negative 12. So that's that. Once it gets to 0 degrees, then it's going to phase change. So it's receiving energy. That's why we have the positive here. It's receiving energy, mass of the ice cube times latent heat of fusion. Once this ice cube becomes water, though, right, that all those water molecules that are at 0 degrees have to be warmed up all the way to 16. So the final temperature would be 16 degrees. The initial temperature would be 0 degrees. And so we have that for our temperature. And so this is just with the portion of the ice cube. Now, if we look at the aluminum cup, that's going to have the influence there. The final temperature is going to be 16, and then the initial temperature is 18, right? And then for the water itself, it started at 16. No, I'm sorry, it started at 18 and then finished at 16. So final temperature minus initial temperature. And yeah, after that, we can figure out what MI is essentially. That's what we want. What is the mass of the ice cube, which is the unknown here, right? Which are all the same thing. So once you distribute all the way in here with this and with this, you can get it in terms of MI and then solve for MI. So why don't you go ahead and finish this one up. Go ahead and pause the clip and complete the rest of this, and then you can check, make sure you're all set, and hit play when you're ready. Okay, so here's all of our variables. This is all the things that need to be in there. And, we'll we'll factor our values in there. We should end up getting an MI of 0.008236 kilograms. And, final temperature of 16 degrees. And so, so we've got that there. All right, so in this one, we have water that's poured into an insulated container that has ice in it, and the initial temperature of the ice is negative 25 degrees Celsius. The initial temperature of the water is 5 degrees Celsius, and the final temperature of the water and ice together is negative 15. So in this case, this water, as it gets poured in here, it actually freezes, and then the whole thing becomes ice. So this is a little bit different because in the last one, we had the ice cube actually melting, right? In this one, the water that's being poured in there turns into ice, and so we have to consider that. So when we set up the sum of the cubes in this one, we have to think about the water's transition to ice, and when that happens, the water itself is actually cooling, and because it's cooling, that's where we actually need to get it from, in this case, it's at negative, where does it, oh, it's at 5 degrees, and the water's got to become 0 degree water, right? So 0 minus 5, final temperature be 0 degrees, initial temperature of this water is 5 degrees, it's got to cool down to 0 degrees, and then it's got a phase change, right? And so in the phase change, we also need a negative, so it's going to be negative MLF because it's actually cooling, it's not heating like on the last one. And so when we set up our sum of the Q's here, we have the negative here because that water itself is going to phase change and cool and freeze, and that's why we have the negative there. And then we have the temperature right here, 0 minus 5. This will also become negative because 0 minus 5 will be negative 5, and we multiply those in. And so this is kind of the reverse of the last situation, and this may be one of the more important things to remember out of the entire lesson here, where, you know, we have to have the negative here because, you know, it's losing that energy. So we'll multiply those in, and we get the mass of the water of 0.0294 kilograms once we factor that out, or factor those in and calculate those out. So when we talk about conductors versus insulators, this is an important consideration too with this unit. If you look at this picture, we have some good examples of conductors and insulators. And the skillet is an excellent conductor. It's conducting, you know, energy from the plate to the food there. But then, you know, he's protecting his hand with this insulator that, you know, you have this glove here. And what's a glove, you know, filled with? You know, sure, there's insulation in there, but it's filled with a lot of air. Air is actually a great insulator. It doesn't transfer energy very easily. So if you have a thermos, a lot of times what they'll do is they'll just have inside a bunch of air. You got your liquid in the middle, you know, you got your cap on top, but, you know, all around this is just air, and it's a good insulator. So transfer of heat by touch we consider as conduction. So that's one way that we transfer energy. And this is a picture of a burner that is heating up a metal bar. And what's happening is these molecules in here are hitting the other ones, and then they're hitting these, and then they're hitting these, and then they're hitting these, and then they're hitting these. And it transfers this energy all the way through. And that's by touch, by conduction. And so we can look at that in terms of, you know, touch by calculating this, and this can be a very powerful example here, where, you know, if you have a hot object and they're touching by a certain, you know, in this case, a certain surface area and over a certain length to a cooler area, you know, it's going to transfer energy at a certain rate. And so we have the heat in joules, the heat flow in joules, we have the time in seconds here, we have the thermal conductivity K in second meters degrees Celsius. We have the temperature of the hot side, and then we have the temperature of the colder side. So, you know, in other words, this could actually be, you know, two rooms. You have, you know, one room here, and then next to that you have another room. And so these are two separated rooms. Trying to draw three-dimensionally there, you know, so this is separated by a wall, let's say, and, you know, the length between the wall is going to be a certain amount between here, L. You know, the area is going to be a certain amount here between them. This hot room is going to have a certain temperature. You know, if this was T1, and then this is cooler temperature T2. This wall has a certain conductivity, right, in K, so a certain insulation. And then what you get is a certain amount of joules per second of energy transfer, and that should remind you of watts, right? That should be, you know, joules per second is a watt, and that's the actual, you know, transfer of energy, thermal energy from one to the other as it goes, you know. And in this case, this would be, you know, if you had a hotter object, colder object, and then in between some sort of substance that's transferring that object through conduction, you know, you can measure that. And so, you know, there's lots of different types of thermal conductivity. Some conduct things much easier than others, and so we could look at different things here. Silver is an excellent conductor, right? Whereas wood is a very poor conductor. So, you know, and then wool is a very poor conductor. And then look at here at air. Air is a really poor conductor, and then, so that's why, you know, these you see, you know, on Arctic explorations, these people have these huge huge jackets, right? The huge jackets, and there's their little head here, right? So their jackets are huge, and so you have a lot of air inside, right? You have, other material, but you got a lot of air in there, and that keeps the person warm. Igloos are a great example, right? So you have this whole layer here, L, and you have the area, surface area of this, and so you could actually figure out the rate of thermal transfer in and out of this. And this would be a good insulator, and you can see that these guys are getting out of the elements in this igloo. So let's take a look at this example. We have two rooms that are separated by a brick wall that's 0.4 meters thick. Temperature of one room is 15 degrees Celsius, the other is 25 degrees Celsius. The wall is 10 meters long by 10 meters high, and we have brick, and this is the conductivity brick. And we want to figure out what is the heat flow rate, so in other words, how many joules per second are going to be passing through. And then part B, how much heat is transferred in 5 minutes between the rooms. And so, yeah, why don't you go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so here's our wall, 10 by 10, 0.4 meters thick, and we end up getting a heat flow rate of 2100 watts or 2100 joules every second. So that's how many joules every second are going through. So in other words, in 5 minutes, right, we know energy is, how much, or power rather, is how much energy in a period of time. So if we have 5 minutes, then, and we have a certain power rate, we can figure out how much energy in 5 minutes. And so we can do that. We'll multiply the energy times the temperature, and we should get, that's 300 seconds there. So this is how many joules are going to be transferred, 630,000 joules every second that are going to pass from one to, or, pass from one side to the other side of this wall. So with this house here, you can see that there, are different areas where thermal energy is being transferred out of. You got your windows, and then the side of the wall, and then the top of the house. And so, as construction or designers and, folks making the homes, they have to pay close attention to that, and to minimize the transfer of energy in or out depending on the needs. So thermal insulation is rated for a certain R value, and the length per thermal conductivity we deal with there. So, we have the different, different substances here. R value of glass here is 1, whereas you have fiberglass, which is higher, and then other substances. If you notice here, like with this insulation R of 30, that's much higher. And so, so the different thermal insulation is used for, different situations. And so, as you consider, the thermal conductivity of these different substances, some transfer energy more effectively than others. And so, in this case here, there's just different uses or costs, right? You have bigger windows, you can have, more energy loss.